The running time of an algorithm is critical for understanding its efficiency, especially as input sizes grow. By analyzing the order of growth, we can determine how performance scales and compare different algorithms. For example, merge sort has a worst-case running time of theta, n log n, which becomes faster than insertion sort's theta, n squared, as input sizes increase. This focus on growth rate simplifies analysis by ignoring lower-order terms and constant factors that have minimal impact for large inputs. This abstraction helps identify algorithms that perform better when scaling up, which is essential for real-world applications. Exact calculations of running time, like those for insertion sort in Chapter 2, are often unnecessary. Once input sizes grow, constant factors and minor terms are dominated by the leading term, making asymptotic analysis efficient. By focusing on the dominant term, we gain insights into scalability and efficiency, enabling better decisions in algorithm selection. This chapter explores these concepts, providing tools for characterizing and comparing algorithms effectively. Asymptotic efficiency examines how algorithms perform as input sizes grow indefinitely. It focuses on dominant trends, which indicate how running time scales. For instance, an algorithm with theta, n log n, growth will generally outperform one with theta, n squared, for large inputs, making it the better choice in most cases. This perspective is crucial in fields like data analysis and computing, where scalability often determines success. By abstracting away hardware-specific details and constant factors, asymptotic efficiency highlights an algorithm's core performance characteristics. This simplification allows us to evaluate algorithms independently of implementation nuances. As a result, it becomes easier to identify solutions that are both efficient and scalable, ensuring robust performance across varying contexts. Simplifying algorithm analysis often involves using asymptotic notation, which concisely describes growth rates. Three main types of notation are introduced: O notation, which gives an upper bound, ohm notation, which provides a lower bound, and theta notation, which describes a tight bound. These notations focus on the dominant term of a function, enabling clear comparisons of algorithm performance. For example, theta notation is particularly useful for analyzing worst-case scenarios, like insertion sort's running time of theta, n squared. The chapter also explores the formal definitions of these notations to ensure accuracy and consistency in their use. Additionally, it reviews common functions like polynomials, logarithms, and exponentials, which frequently appear in algorithm analysis. By understanding these tools, we can systematically evaluate scalability and efficiency, making informed choices about algorithm design. A practical example of asymptotic notation is seen in the analysis of insertion sort. Its worst-case running time involves a complex expression with multiple terms. Using asymptotic notation, we simplify this to focus on the dominant term, leading to the characterization of its running time as theta, n squared. This simplification highlights the scalability of the algorithm and allows for easier comparisons with other sorting techniques. By discarding lower-order terms and constant factors, asymptotic notation captures the essential performance characteristics of algorithms. This abstraction provides a universal framework for analyzing and comparing efficiency, ensuring that our evaluations remain consistent and meaningful even for large input sizes. Asymptotic notation is versatile, extending beyond running time to other aspects like space usage. It provides a standardized framework for comparing algorithms across different dimensions of performance. For example, just as we use theta notation for time complexity, we can apply it to space complexity. This flexibility ensures that asymptotic notation remains relevant across a wide range of computational problems. By abstracting implementation details, asymptotic notation focuses on fundamental algorithm properties, allowing for meaningful comparisons. This emphasis on scalability and efficiency ensures that the analysis is robust and applicable to both theoretical and practical scenarios. As such, it remains an indispensable tool for understanding and designing algorithms that perform well in diverse contexts. O notation, or big O notation, describes an upper bound on an algorithm's growth rate, capturing the maximum performance under worst-case conditions. For example, a function is O n cubed if it grows no faster than n cubed for sufficiently large inputs. This focus on the highest order term simplifies analysis by ignoring lower order terms and constants. O notation is crucial for evaluating how well algorithms handle worst-case scenarios, ensuring that their scalability is well understood. Importantly, O notation allows flexibility. For instance, the function 7n cubed plus 100n squared, 20n plus 6 can be described as O n cubed, O n to the power of 4, or O n to the power of 5, though the tightest bound is O n cubed. By emphasizing the dominant term, O notation enables clear comparisons and robust evaluations, providing a reliable metric for worst-case performance. Ohm notation, or big omega notation, describes a lower bound on an algorithm's growth rate, indicating the minimum performance under the best conditions. If a function is ohm n cubed, it grows at least as fast as n cubed for sufficiently large inputs. This ensures that even in ideal scenarios, the algorithm requires a certain level of resources, highlighting its inherent complexity. For example, the function 7n cubed plus 100n squared, 20n plus 6 can be described as ohm n cubed, ohm n squared, or even ohm n, with ohm n cubed being the tightest bound. By establishing this lower limit, ohm notation ensures a realistic understanding of an algorithm's efficiency and provides valuable insights into its foundational behavior. Theta notation, or big theta notation, provides a tight bound on an algorithm's growth rate, combining upper and lower bounds into a precise measure. If a function is theta, n cubed, it grows exactly at the rate of n cubed for large inputs, capturing the algorithm's true performance. This makes theta notation the most accurate tool for describing scalability and efficiency. To prove theta, Fn, it must satisfy both OFn and OMFn. For example, 7n cubed plus 100n squared, 20n plus 6 is theta, n cubed, as it meets these criteria. Theta notation provides a complete characterization of growth, enabling precise comparisons and deeper insights into algorithm efficiency. It remains a cornerstone of algorithm analysis, ensuring clarity and understanding performance. The analysis of insertion sort demonstrates how running times are calculated and characterized. The outer loop runs n1 times regardless of the input, while the inner loop's iterations depend on the data being sorted. For each I in the outer loop, the inner loop may run 0 to i1 times, depending on the number of shifts required. In the worst case, the total inner loop iterations approximate n1, which is less than n squared. Since each iteration of the inner loop takes constant time, the total running time in the worst case is proportional to n squared, leading to a time complexity of O(n squared). This analysis emphasizes the importance of understanding loop interactions and scaling when evaluating algorithms, providing critical insights into their behavior under various conditions. The worst-case analysis of insertion sort reveals its limitations for large datasets. Its running time is ohm n squared, meaning that for sufficiently large inputs, there exists at least one input configuration requiring at least cn squared operations, where c is a positive constant. For instance, if the largest n/3 elements are in the first n/3 positions, they must shift to the last n/3 positions, requiring at least n/3 n/3 equals n squared/9 operations. This result highlights insertion sort's inefficiency in the worst case. While it performs well for small or nearly sorted inputs, its quadratic growth rate restricts scalability. Understanding such limitations is vital for selecting appropriate algorithms, especially when efficiency is a priority for handling large datasets. Insertion sort's performance can be summarized by its upper, lower, and tight bounds. Its upper bound is O(n squared), which means the running time will not exceed a constant times n squared for large inputs, ensuring a worst-case estimate. Its lower bound is ohm n squared, meaning that there exists an input configuration where the running time grows at least as fast as n squared. These bounds provide both an upper and lower limit on performance. When combining these bounds, we conclude that insertion sort's worst-case running time is theta, n squared, capturing its growth rate precisely. It's important to note, however, that this applies only to the worst case. In the best case, such as when the input is already sorted, the running time reduces to theta, n. This analysis highlights the importance of considering both best and worst cases when evaluating an algorithm's efficiency. Asymptotic notations are defined formally to ensure accurate and consistent application. For O notation, Fn is in OGn, if there exist positive constants c and n0 such that 0 less than or equal to Fn less than or equal to cgn for all n greater than or equal to n0. This describes an upper bound on the growth of Fn. Similarly, ohm notation is defined as, Fn is in ohm Gn, if there exist positive constants c and n0 such that 0 less than or equal to cgn less than or equal to Fn for all n greater than or equal to n0, representing a lower bound. Theta notation combines these bounds, Fn is in theta, Gn, if there exist constants c1, c2, and n0 such that 0 less than or equal to c1 Gn less than or equal to Fn less than or equal to c2 Gn for all n greater than or equal to n0. These definitions provide a rigorous mathematical foundation for analyzing algorithms, ensuring that growth rates are properly characterized. They form the basis for comparing and evaluating performance across different scenarios. Asymptotic notations have several key properties that enhance their utility. One is transitivity. If Fn equals theta, Gn, and Gn equals theta, Hn, then Fn equals theta, Hn. This also applies to O and ohm notations, allowing for logical chaining and comparisons. Another property is reflexivity. Any function satisfies Fn equals theta, Fn, Fn equals OFn, and Fn equals OMFn, reflecting that a function bounds itself. Symmetry is another useful property. If Fn equals theta, Gn, then Gn equals theta, Fn, making these notations bidirectional. Additionally, transpose symmetry holds: if Fn equals OGn, then Gn equals Fn. These properties ensure that asymptotic notations are reliable and consistent tools for algorithm analysis, enabling clear comparisons and robust evaluations. Asymptotic comparisons can be likened to real number relations.
For example, Fn equals Ogn resembles a less than or equal to b, Fn equals Gn corresponds to a greater than or equal to b, and Fn equals eta, Gn, is like a equals b.
Similarly, Ogn and omega, Gn, represent a b, respectively. This analogy helps illustrate the relative growth rates of functions. However, not all functions are asymptotically comparable. For instance, n and n(1 plus sin n) cannot be directly compared, as the exponent in n(1 plus sin n) oscillates between 0 and 2. This limitation emphasizes the importance of context when applying asymptotic notation. While these tools are powerful for most scenarios, understanding their boundaries is crucial for accurate algorithm analysis. Common mathematical functions play a central role in algorithm analysis. Monotonicity describes functions that consistently increase or decrease, which helps in predicting trends. The floor and ceiling functions, which round numbers down or up, are often used in discrete calculations. Modular arithmetic, dealing with remainders, is critical in areas like cryptography and hashing. Additionally, polynomials, exponentials, logarithms, and factorials frequently arise in complexity analysis. Logarithms, for instance, describe the growth of divide and conquer algorithms, while factorials are common in combinatorics and recursion. Understanding these functions and their properties provides essential insights into algorithm efficiency and scalability. Asymptotic notation is a cornerstone of algorithm analysis, offering a concise way to describe scalability and efficiency. By focusing on dominant terms, it simplifies complex growth rates into comprehensible bounds. This chapter introduced O notation, ohm notation, and theta notation, each serving a specific role in characterizing performance. These tools enable precise evaluations and informed decision-making in selecting algorithms. In practice, asymptotic notation abstracts implementation details and highlights an algorithm's fundamental behavior. This abstraction ensures that analysis remains relevant across different contexts, from theoretical research to real-world applications. By emphasizing growth rates, asymptotic notation allows developers to choose algorithms that perform well on large datasets and optimize performance for long-term efficiency.